Determine conditions for when a light bulb will be turned on in a switching circuit. So I have two badly drawn light bulbs here, right? One that is dark, just empty, and one that is yellow, which means it's lit up. So let's talk about light bulbs. If I have these two circuits here, like we have P and Q, both P and Q must be true for the light bulb to turn on. So think about it. If they're both true, that means they are closed. It completes the circuit. The light bulb turns yellow and it's on. So that would be P and Q. Now, depending on the circuit, it could change the original state of P and or Q, right? So it could be that not P is what is true or whatever. So you really have to kind of think about the entire circuit and how it all works to determine what has to be true for this to work. And you're now thinking, I don't know what you're talking about. Well, let's play. So now we have ourselves a circuit. So what combinations of P and Q will turn the light bulb on? So we have ourselves a circuit, and you see our non-lit light bulb at the end, right? It's just an empty shell of a picture here. So when we're working through this circuit, what does this mean? And we're talking about the truth value of P and Q. So let's think about this, just this circuit. Okay, so as we work through, I have not P, and I have Q, and they are joined by and. All right? Now, we know that we need both of these to be true for the light bulb to turn on. So let's think about this. Okay, we have not P and Q. If we think about our truth table, actually, I'm going to give myself more room. Okay, so thinking through this, we know that the truth table starts true, true, false, false, true, false, true, false, right? We give ourselves our starting point. Now we negate P by taking the opposite truth values. And now we can say, okay, we are talking about not P and Q. They both have to be true. So false, true. I look at the first one, that's false. False, false, true, true, false, true, false. That means this line right here is where my piece is true, right? Because we know it has to be true for the light bulb to turn on. Therefore, P has to be false and Q has to be true. When P is false and Q is true, this circuit becomes true. And that's what we want. We want the circuit to be true so that the light bulb shows up. So if P is false and Q is true, my light bulb will light up. That's what I know based off of the truth table from the next page, right? That's the idea that we're looking at of what makes this true. Okay, let's look at another one. What combinations of P and Q will turn the light bulb on? Okay, so again, think about what this means. I have not P, I have not Q, joined by and. And again, we need this to be true for the light bulb to... Okay, so P, Q, not P, not Q, and we are looking at not P and not Q. Okay, so true, true, false, false, true, false, true, false. Let's negate P, false, false, true, true. Let's negate Q, false, true, false, true. Whew. Okay, now the and, not P and not Q. I'm looking at these two lines, not P and not Q. They both have to be true. So false, 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 true, true, false, true, true. Here it is. This is the line. This is where my circuit is true. So go back to P and Q. What do you know about them? They both have to be false. So if P is false and Q is false, then my light bulb will light up because the circuit will be true. Right? Does that make sense? I hope that makes sense. This is why I love truth tables. I'm a very visual learner. When you create the truth table and you're looking at that last column, there's only one spot where it's true. So when we're looking if we care about the P and the Q value, go back to those original columns. What do you know about the truth values of those original columns? That's what has to be true to make that light bulb light up.